Topic 6 is the biggest short question topic, appears in 6 plus papers. Let's break it into small sub skills, each with real examples. Take your time here since it recurs a lot. Okay, so topic 6 is roots of equations. Step 1, the master tool, relation between roots and coefficients. For any cubic equation, x cube plus px square plus qx plus r equals 0 with roots alpha, beta and gamma. There are three golden formulas. Memorize these. They unlock almost everything in this topic. So alpha plus beta plus gamma is equal to minus p. Alpha, beta, gamma equals minus r. Where is the third golden formula? Where do these come from in plain English? If alpha, beta, gamma are roots, the equation can be written as this. So if you expand this out, multiply everything, you get something like this. Now this is equal to p. So this alpha plus beta plus gamma is minus p. Alpha, beta, gamma is minus r. And q can be written like this: alpha beta plus beta gamma plus gamma alpha. Notice here it's plus minus plus minus. Okay, compare this term by term. As you can see, they did it like this. You don't need to rederive this every time, just memorize the three boxed formulas above. For me it would be easier to derive anyway. So sign pattern, trick, alternatives, plus then matches, then alternatives again. But honestly, just memorize the three lines directly, it's faster. Okay, real question: if alpha, beta, gamma are roots of this equation, then find 1 upon alpha, summation of 1 upon alpha. So summation of 1 upon alpha means 1 upon alpha plus 1 upon beta plus 1 upon gamma. Sum of reciprocal of all roots. Okay, so step A, combine into one fraction. If you do basic algebra, common denominator, the common denominator would be alpha, beta, gamma, and numerator would be beta gamma plus alpha beta. So this was basically q and this is minus r, so this can be written as minus q upon r. Two lines answer once you know the formula. Step 3, forming an equation when you know one of the complex roots. So paper 4, 5, 6, 9, this repeats a lot. Find equation whose one root is 2 plus 3i or 2 minus 3i. Key fact you must know: for equations with real coefficients, no I anywhere in the original equation, complex roots always come in conjugate pairs. So if 2 plus 3i is a root, then 2 minus 3i must also be a root, automatically guaranteed. Question: find an equation whose one root is this. Since complex roots come in pairs, the other root is its conjugate. Now step B, if alpha is this and beta is this are the roots, we build the equation like this. So it would be quadratic equation, so expand this, but here's the shortcut instead of fulfill. Notice sum and product, same idea as step 1 but just for two roots. Okay, then sum alpha plus beta are the sum equal to this, then this is going to cancel out, we're left with 4, the I parts cancel out, product alpha beta. This is a difference of squares, so a plus b, a minus b is a square minus b square, so this would be 2 square minus 3i square equals this thing. So remember, iota square I square is just minus 1. So this is minus 1 times minus 1 is plus 9. So 9 plus 4, 13. Plug sum and product into our equation that we had. Into this equation, we get our polynomial. So for 2 minus 3i version, exact same method. Sum is still 4. Conjugate pair is still 2 plus 3i. Product is still 13. Multiplication doesn't care about orders. Same answer. So really these two different looking questions are the same question. Okay. Step 4. Given one root, solve the whole cubic. Paper 5, 6, 9 and 10. So given one root, solve the whole cubic. So minus 6 is the root of this. Solve it. Now idea, if we already know one root, we can use synthetic division, topic 5, to divide it out, leaving a simpler quadratic that we solve normally. So given minus 6 is root, then remainder is 0. Then solving with synthetic division method, coefficients are 1, 2, minus 17 and 42, and minus 6 is the root, so a is minus 6. Use synthetic division with a equals minus 6 and we get 0 as remainder. Confirms minus 6 is the root. Go check. And now we have minus 6, 24, what? Wait, we have 1, minus 4 and 7. So x square minus 4x plus 7, square minus 4x plus 7 equals 0. 1 degree lower as always. So now step C is to solve this quadratic using quadratic formula. We have our coefficients using the quadratic formula. We now have 2 of our roots. So full answer, the 3 roots are these. Okay, so quadratic formula is important. I actually didn't remember what's that called. Anyway, so step 5, roots in arithmetic progression, AP. Paper 6, solve for this polynomial roots in AP. So roots are in AP, arithmetic progression. So alpha, then alpha plus 1 is it. Anyway, so what does roots in AP mean? The 3 roots have equal gaps between them. Okay, equal gaps, not like consecutive numbers, but equal gaps between them, like 3, 5, 7 gaps of 2 each. We can always write such roots like this: a minus d, a and a plus d. Nice. So why is this useful? Because a minus d plus a plus d is 3a. The d cancels out immediately when you sum them. This gives us a superfast using step 1's formula. So now roots are this. Sum of the root is 12 minus p, where p is minus 12. Sum of the root equals minus p and p is minus 12. So the sum is 12. So this must be equal to 12. 3a equal 12. A is 4. Since a is 4 is a value, we found a is one of the roots, the middle one. Then x equal to 4 must satisfy the original equation. Let's use this as our known root and apply step 4 synthetic division again. So verify plus divide using a plus 4. So now our coefficients are these. We're going to divide with synthetic division. It completely cancels out. So remainder 0. It works. Confirms 4 is indeed a root. And new equation we have is this. Tab D, quotient. Factor this. Find two numbers that multiply to 7. Two numbers that multiply to 7 and add to minus 8. So minus 1 times minus 7 is it, and add to minus 8. Yes, so minus 1 and minus 7. So this can be written like this. Final answer, roots are 1, 4, 1, 4 and 7. 1 and 4 हमने पहले निकाला था and 7. Okay, so and yes, check 1, 4, 7 has equal gaps of 3, confirming APs. This was a good question, good enough question. Okay, so step 6, diminishing the roots by constant. Diminish roots of this by 4. What do you mean? Like subtract 4 from the roots? What does diminish root by h mean? We want a new equation whose roots are each h less than the original equation's roots. In other words, if original roots are alpha, beta, gamma, and delta, we want new equation whose roots are alpha minus h, beta minus h, gamma minus h, and delta minus h. The trick, this is done using repeated synthetic division by the value h, not minus h. This trips people up, so remember to diminish by h. Divide using plus h in synthetic division repeatedly. Since this is a long, repetitive mechanical process, 4 rounds of synthetic division for a 4-degree polynomial, it's only worth 2 marks per your rule number 1 and 4. This is low priority question. I'd only fully practice this if you have spare time. After nailing the high frequency stuff above, let me know if you want the full worked steps. Otherwise, let's keep moving. I don't want to do it actually. Not right now. What do you guys think? Maybe just to put it in the video, I can. Anyway, so step 7, prove x raised to the power 2n minus 1 equals 0 has only 2 real roots. So this appeared 4 times for papers. High priority setup. We want to show that no matter what n is, the equation x raised to the power 2n minus 1 equals 0 has exactly 2 real solutions. All the rest are complex. So step A, rearrange the equation. So now this can be written like this. Think about the real values of x could satisfy for it to be equal to 1. Since 2n is always an even number, any n times 2 is even. Think about the function y equals x raised to the power 2 and key insight for even powers. This is always greater than or equal to 0. Always. Squaring type powers can never go negative, and x to n only equals exactly 1 when x is equal to 1 or x is equal to minus 1. Let's verify. Yes, it works. If x is any other real number, let's say 2 is some huge number way bigger than 1, not equal to 1. If x is between minus 1 and 1, it becomes a tiny fraction less than 1, never equal to 1. So amongst all the real numbers, only these two satisfy the equation. Formal proof style writing, this is what to actually write in the exam, not the intuition. So since this x raised to the power 2n can be written like this, x squared raised to the power n minus 1, and using factorization an minus bn pattern. Actually, here's a cleaner way. Factor x to n minus 1 as a difference of squares, treating it as like this. So now this can be a square minus b square. This can be written as a plus b a minus b. So either this is 1 or this is minus 1. But what did we need to show? We needed to prove that this has only 2 real roots. This equation has only 2 real roots. So now this equation has 2 roots amongst the 2n. Total roots of this, a degree 2n polynomial has exactly 2n roots total, counting complex ones. This is the fundamental theorem of algebra. Just accept this fact. Only x equals 1 from this when raised appropriately, and x equals minus 1 when give real values. Every other root involves complex numbers. These come from nth roots of unity, which are complex except for these two cases. Hence this equals 0 has exactly 2 real roots, and remaining 2n minus 2 roots are complex. How would we prove this? But for exam purpose, write step B's verification style reasoning. So this satisfies it, and no other real number can. Is honestly sufficient and easier to remember. Also, this is just a 2 marks question. So what would the examiner expect of me? Is honesty sufficient and easier to remember than factorization approach? Use whichever clicks for you. I can do this thing, but only up to here only. What the hell? Anyway, so master summary, what we did. Um, let's actually do that. Roots in AP के बाद आया था ना. Diminishing roots. Let's do this question also. This was a heavy topic. Takes a breather if you need it. Take a breather if you need it. Anyways, this covers roughly 10 different question, 9 subpart across 6 papers. So this topic was important actually. Let's do this. अगर easy हुआ तो otherwise I'll skip for now. Let's do it properly. This is the low priority one I mentioned, but since you wanted, let's build it from zero. So diminishing root by constant. यहाँ तक तो हो गया था. Why would anybody want this? It's a stepping stone used in other techniques like removing terms from equation, but for our purpose it's just a mechanical exercise you need to know how to execute. So the trick, substitution. If we let y equals to x equal what? So we had these roots and we need an equation with diminished roots by h. So now the trick, if we let y equals x minus h, a new variable y which is just shifted down by h, which is x shifted down by h, then x equals y plus h. If we substitute x equals y plus h into the original equation and simplify, we get a brand new equation in terms of y, and this new equation's roots are automatically h smaller than the original x's roots. That's literally definition working out the problem. Substituting this directly and expanding by hand is a nightmare. Imagine expanding this painful. So instead we use a shortcut, repeated synthetic division. The shortcut method, this is what you'll actually do in exam. Rule: to diminish the roots of a degree and polynomial by h, do synthetic division by h repeated n times in a row, each time dividing the quotient from the previous step, not the remainder. Collect all the remainders as you go. These remainders become the coefficient of a new equation, and read in reverse order. Last remainder found equals first coefficient after the leading term. So let's just do it and you'll see the pattern. Okay, our question, we need this. We need a new equation with roots diminished by 4. So coefficients of the original equation are these. This is degree 4 polynomial, so we'll do synthetic division 4 times, once for each degree. H equals 4 throughout. Okay, so division 1, divide this by a equals to h. We will get minus 9 as remainder, and this as the first coefficient. Similarly, doing this 4 times, remainder and coefficient as you see on the fourth. Assemble the final answer. We stop here because we have done it 4 times, matching the degree of the original polynomial. We collected 4 remainders along the way. So now the rule for assembling the new equation in terms of y, where y equals x minus 4, is built by reading the remainders backwards. Last one found is the first coefficient after leading one. So this is y4, y4, what? So no coefficient for y4, r4, r3, r2 and r1. Okay, fine. So plugging in our numbers, we get this. This is the final answer. The equation whose roots are
each 4 less than the roots of the original equation. That was easy actually. Step 6, why does reading backward works? Quick intuition. Skip if you just want the method. We can read it, it's short. Okay, think of it like peeling an onion. Division 1 finds you the innermost piece of the shift, the constant term the contribution, and the each subsequent division builds up the next layer outwards. So the first remainder you calculate ends up being the last piece of the final answer, the constant term, and the last remainder you calculate becomes the coefficient closest to the leading term. It's a bit like a snack. First in, last out. Don't worry about the proving this, just trust the pattern. It always works this way for diminishing roots. Anyway, so it's done. You can read the quick recap. I won't. Fast way to remember the order. The last remainder you compute was right after the leading y term, and the first remainder you ever computed ends up as the very last constant term. That's called mechanical process. 4 rounds of skill you already know from topic 5, and the topic is complete.